All right, hello everybody. We are very close to the end of our topic or part two, which is mainly probability in different forms. Let's have a look at what is next. Now, we didn't quite finish our discussion on probability distributions. So we did exercise 7.2, and if you have not, go and watch that video first. We just want a little more practice with another kind of more practical exercise in 7.3. Let me just see if that's big enough. It's okay. Just to solidify the idea and the steps that we go through. So let's read exercise 7.3. Consider the following game of chance. Two balanced, six-sided dice are rolled. If double sixes are rolled, the player wins $10. If doubles of any other number is rolled, the player wins $5. But if the two numbers on the dice are different, the player doesn't win anything. Single play, standard question probability distribution. Now I've changed the wording here a little bit because it's just sort of getting us to discuss it. We essentially want to do everything for this question. Exercise 7 point. What did I just say? I just said it's 7.3. Okay, so now, like I said before, crucial at the start to be very aware of what is the experiment, what is the action that I'm doing, and what is considered an outcome to this experiment. Those two things in combination really decide everything moving forward. So we're rolling two dice, six-sided, fair, balanced dice, and we want to see the two numbers. Okay. So my experiment. Now, I didn't quite say it right, but one thing at a time. So whether I write these two out or not, I do want to be aware of them. Experiment, roll two dice. Let's say red and blue, just in case I need it. Now, in this situation, what I'm actually interested in as an outcome is the money that the player is going to win. Can win $10, can win $5, or of course can win nothing. So the outcome is the, let's say, prize money. But of course, there's a little bit of a gap between these. However, these two together are just summarized in what we call a random variable. So we're going to say let x represent the prize money from rolling two dice. Now, of course, there's more in here. The possible values of x, listing that would clarify a little bit more what could happen. And then we clarify it even more by showing and figuring out what the probabilities are. But we're building up, explaining the experiment in its detail. So first of all, I could, best case to worst case, win as a player $10 or $5, or of course I could win nothing. But that covers everything that could happen. Now, how that could happen plays a big role in the experiment. It's not the experiment, yes, I suppose, in the probabilities. So let's give this a heading here. probability distribution, that is an S, I know. My writing is so clear. Distribution of X. Remember, X captures and represents the experiment and outcome and the whole thing. If I change what I do, rolling 3 dice instead of 2 or something else, then it's a new combination, new random variable. If I still roll 2 dice, but my prizes are different or something else in terms of the actual outcome, that's a new combination, new random variable. So I'm going to just do this in table form. It's simpler and visually pretty good. You see the summary, and I don't have that many, right? So I can have different values of X, and then I'll look at the probability of X equaling those values. That is just a different way of naming the different events. So I can go 10, 5, 0, giving myself some space here for possible fractions. So now let's see, I rolled 2 dice, so the possible pairs that I could get there are 36 of them. I have to go to the pairs of numbers because those are equally likely results. So even though my outcomes are officially, my outcomes are the prize values, the dollar amounts that I could win. When I calculate a probability, I have to conceptually alter it a little bit so that I can look at related outcomes that are equally likely. It's not the probability of getting 10 isn't 1/3 because there are 3 possible outcomes and I have one of them. These are not equally likely. I need to shift how I look at this so that I can look at equally likely things, or I can't calculate the probability in this basic sense. So that's why we look at pairs of dice values giving me this outcome. And I think there's only one, isn't there? I have to roll double sixes. So 1 in 36. Out of the 36 possible pairs, how many will give me 5 as a prize? Well, doubles of any other number. So double 1, 2, 3, 4, or 5. So there are 5 other doubles. Now please note, this 5 and this 5 are completely different 5s. Talking about and referring to completely different things. And then 0, I don't have to actually count it directly because I know that if I've covered all the possible values of X, all the possible outcomes that could happen, adding up the probabilities has to equal 1. So 36 out of 36. So the fraction that's missing out of 36 has to be 30. It's a little bit of a risky move, I suppose, because I'm relying on my first 2 probabilities being correct and then exploiting the property of a probability distribution that all the probabilities add up to 1. But often with the table, one of them is a little bit more of a hassle to count and list 30 possible pairs that will result in losing. I could just sort of exploit that property and find one of the missing probabilities because they have to add up to 1. Okay. So all of this now clearly, well, to a degree, clearly describes what could happen here. So in this exercise, we don't worry about ticket price like the previous raffle question. So read the wording and be sure of what they are interested in. We're just interested in the prize. We can still analyze this game because just looking at these probabilities, yeah, okay, of course, the best prize is going to be less likely than losing, but that probability in combination with the money that I can win, how do those all work together to determine if this game is worth playing or not. That's where the first measure to try and help us analyze this game is the expected value. And of course, it's the expected value of the random variable. The random variable is the representative of this whole situation. And we're going to write it as E square brackets X. That's how it's done. That's how I'm going to do it. Very simple calculation. Take each of the possible values of X one at a time and multiply with the associated probability. Then I'll take the next one, multiply by its associated probability, take the next one, multiply by its associated probability, and I'll get an answer. Let us do it in the chat. Now, I don't need to do the last one, right? Because it's just going to be 0. 0 times anything is 0. So for convenience, I won't actually type that. So I have 10 times 1 divided by 36 plus 5 times 5 divided by 36, and I don't need the 0. Don't need the 0. It won't give me any different answer. And we get 0.97, I'll just say. Now remember, this is a dollar amount. So 97 cents is expected. Now, like in most practical situations, if I perform a calculation, it's only worth doing if it tells me something, if it gives information that I didn't have before. And the expected value certainly does that. But I need to interpret it, right? I need to interpret it. So there are two interpretations. One is a little tricky to really intuitively get. It's really just an indication of where does this sit. I'm not going to write it out because it's weird. I'll just say it. As soon as I write it out and say a full sentence, it doesn't sound right. And I'll say why in a second. If I look at my range of 0 to 10, remember this game doesn't cost me anything, which is why I can't get anything negative. However, this is 5, this is 2, and a 1. Expected value sits right there close to 0, which I expect, right? It shouldn't be very likely that I win the prize. So I can't necessarily say, well, I can't realistically say, oh, if I play the game once, I expect to win 97 cents, because that's not one of the options I could win. But sitting close to 0 does give me initially an indication that I'm much more likely to lose often than I am to win. But the probabilities sort of told me that already. So it's nice to sort of see where this sits, but it's not really the full interpretation. The better interpretation, or the complete interpretation of the expected value, is in terms of being a long-term average. So let's write it down like this. This is worth a full sentence. If we play this, man, my writing is just horrible. Balance between speed and clarity. If we play this game many times, then we will win 97 cents, let's say on average per game. Or per game, average winning will be 97 cents, which makes sense because I might play once and I might win first prize. So now I have $10 in my hand. Should I keep playing? Probably not. because systematically I'm going to lose way more often, and my average per game winnings will be 97 cents. So if I win, I should walk away, because the more I play, the more the losses will chip away at those winnings. Now, it's a little different from the previous one because this doesn't cost me any money, but I still want to maximize my per game winning, right? If I play more and more and more and it doesn't really improve my situation, it's not worth it. And I can add to this. Let's pretend I am interested in going to the fair and hosting a game like this. I need to know, right? I am now the host of this game. I want to make money, yet I want it to be an appealing game for people. So I don't want it to be obvious that I just want to take your money. So now I've analyzed the situation of this game by choosing a $10 prize and a $5 prize in these situations, exactly like we did it. But I haven't incorporated my ticket price yet. Now I can decide, well, okay, I know if I ask nothing, of course they're going to win money. There's no balance. They're going to win 97 cents on average. So if my ticket price is just more than 97 cents, if enough games are played, I'm going to win money and they're going to lose. For example, if the ticket price is $1, let's say, then the player loses 3 cents, more or less, right? I rounded this. Long term prediction. How long term? That's hard to say. Probably extremely long term, probably. That I could host this. People come, they play hundreds of games, and because my profit margin is so small, I might still lose. But this analysis says that if enough games are played for long enough, this is what's going to happen on average. How long? The expected value doesn't tell me that. There are other measures that can tell me that get fancier, that tell me, well, do I expect results close to this average often, and how close, and things like that, and how extreme up or down can the results be, and that affects how long I need to wait to be assured of getting close to this expected value. But those are more complicated. This still just gives me an idea. Or you can then decide, well, 3 cents profit per game, that doesn't sound like a lot. Let's make it $2. There's now a balance in designing this game between making it not too expensive, so people want to play, they don't feel a dollar is very risky, yet putting the odds in my favor. And there's very nice practical things that come out of this uh, discussion of probability distributions and expected values. How do I analyze this game of chance? Because the probabilities are going to be the same. Let's say this game costs 50 cents to play. The probability distribution looks the same. These probabilities don't change. How do I figure out which side it favors, the player or the host? How do I do it? Expected value is the first step in doing that. So having some knowledge about probabilities, probability distributions, expected values, and these measures just makes me more educated and just better in general. It's a very clear, I hope, practical purpose to these things. And of course, the game could be much fancier. There are much fancier measures that give me more and more information. Of course, what we often do in this course is lay some foundation, some introduction, have a little look. Oh, expected value. Okay. But of course, we can't go all the way, right? That's the whole subject of statistics. It's not a quick discussion, but it gives us a taste. It's a first step for sure, for sure. All right. Let us move on, sort of. Now we have a lot of time. I looked at the schedule and there's actually a ton of time, but we'll just take as long as we take. There are essentially two more things that I want to do. Now, I'm just going to remember, I don't have the slide. I guess I could find it in a video. That's fine. I'll just write it again. Let's remember a previous example. And the one I want to remember, just because we did it, it's easy. It's not a brand new one, is where I rolled two dice and I noticed the largest number of the two. Hopefully you remember that. So let's remember exercise 7.1. I have my random variable. Actually, do I care about a random variable? I guess I do. Let x represent the largest number from two dice rolls. Now, of course, it's excited. I could change the dice, make it more interesting, but there's no need to make a new question here when I'm just trying to introduce another concept. So let's go with something familiar. Two dice rolls. I had my probability distribution. Let's say here, I'll just shorten it because we did do it. Probability x equals a number. And I had values 1, 2, 3. I'm actually going to do two tables here because I don't want it to be too long. We've done it before. I'm just remembering. 4, 5, and 6. So what was it? It was 1 out of 36, and then it was 3 out of 36. I'm just going off memory, right? We don't have to redo this. You can look it up, watch that video again. If you don't remember, this is what we got. And 11 out of 36. Check, they add up to 1. Probability distribution. I'm just splitting it in two so we don't scroll up and down. Okay. Now, in this one, the expected value doesn't perhaps tell me that much, but let's now think about, let me leave this. I'm going to make a new page. Let's think about the theoretical versus the practical side of things. Now, I'm taking a very simple example, fair enough. But even in this example, there's a difference between the practical side of things and the theoretical side of things. The probability distribution is a theoretical ideal that says that if I were to roll these two dice, this guy, for example, can be interpreted on his own in a very similar way to the expected value. The expected value is just an overall measure, but a single probability. How do I interpret this probability? That the largest number is a 3 has probability 5 out of 36. Let's actually calculate that because maybe you don't like the 5 out of 36 fraction form. 5 divided by 36. I can write it in different forms, right? I can write 0.1389 rounded, excuse me, or I can write 13.89%. I round the decimal version to 4 decimals so that when I make it a percentage, I have a couple more decimals, at least 2. So whichever one you look at, it's the probability that 3 is the largest number. Okay, great. What does that actually mean? Remember, probabilities and all of these, and this whole topic is really there to analyze a situation, to convey information. Calculating an oh sorry, I can't speak properly apparently. Calculating a number and then walking away, well, what did I actually accomplish here? That number should tell me something, which means the interpretation of that number at every stage is pretty important for this specific topic. It's not really an academic exercise, and that's it. It's there to tell me about practical situations. We introduce it with simple examples, but that's not the goal. How do I interpret this probability? Very important. You have to be able to do it. Very important. It's a long-term indication of what I expect. And I can have a general expected value interpretation, which says long term, what do I expect for this experiment as a whole? Oops. Or I can focus on a single outcome or anything in between. So let's write this down. Interpretation of this, for example, that if we um, run this experiment, or repeat, let's go with repeat. If we repeat the experiment, in this case, roll 2 dice, many times. How many times? Many. How many is many? More than any number you can think of. Repeat it as many times as we need to, and then maybe more. Then we will get the outcome of 3, which means the largest number is 3, approximately 13.89% of the time. So I want to do it not too specific here. Can we see this on the screen? Let me check. That looks good. Not too specific. Of course, I can be specific for this experiment and say, if we roll 2 dice over and 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 over, then we kind of expect and will get closer to getting largest number 3 around 13.89% of the time. If I only do it a few times, well, then that's really the practical side of things. That this theoretical probability indicates what the chances are, what the likelihood is, what's the breakdown of getting different outcomes in a long-term ideal situation. But if I actually roll the dice, I'm going to do it a few times. Maybe if I'm in the mood, I'll do it a hundred times, a couple of hundred. That's not enough. Okay. So let's focus on this, for example. Let's focus on this 3. So the theoretical side says the probability that x equals 3 is 0.1389, which means 13.89%. Yes, approximately, but it's extremely close, right? So now when I switch to practically doing this experiment, where am I at this one? I can't roll the 2 dice this many times. Maybe, so this requires technically an infinite number of repetitions to get to this 13.89%. Practically, let's suppose we roll the dice or repeat the experiment, let's say 100 times. 100 times. Yes, I know I don't want to do it too few times. I want to do it a good number of times, but I can't sit here all day. So let's go with 100. That's a lot. I'll roll 2 dice 100 times, write down the answer every time. Sometimes I'm going to get 1. Sometimes I'm going to get a 6. Sometimes I'm going to get a 3. So let's suppose we get x equal to 3, let's suppose we get it 20 times. 20 times I got a 3, among other things. Okay? Let's actually have a table here. Let's suppose we got largest number, and then how many times did we get it? So we could get a largest number of 1, 2, 3, 4, 5, and 6. Among our 100 rolls, we got a 3 20 times. We got a 1 2 times. We got a 2 5 times. We got a 4 25 times. I have to make sure I actually get 100 here, right? I'm making this up. Total. How much do I have so far? 7, 27, 52. Okay, so let's say here we got a 5 30 times. How much do I have now? Let me just triple check here. 7, 27, 52, 82. So then 18 times for the 6, right? Is that right? I hope that's right. Let's show it in the chat. Uh, so we have something to look at anyway. 2 plus 5 plus 20 plus 25 plus 30 plus 18. Yay, I can add. Good. Good job, me. So let's suppose this what happens, because I don't know what's going to happen. There's a little randomness there, right? I know some are more likely than others, but that's not a guarantee of getting anything. I could play the lottery and win. It's unlikely. It happens to someone. Could happen to me. Well, okay, probably won't, but it could. Even the winners say, I didn't think it would happen to me. It happens to someone, right? So these numbers are not going to be perfectly fitting what I expect. I get, for example, 20 times. The largest number is a 3. So out of 100, I got 20 out of 100 is the proportion. Proportion, 20 out of my 100 repetitions. That is 0.2. That means I got it 20% of the time. But the probability is 13.89. Why are they not the same? They're not the same because I didn't repeat this. I didn't roll 2 dice infinitely many times. If I did another 100 and another 100 and another 100, this 20% will drift towards 13.89. And the more I repeat it, the closer I'm going to get. It's a slow drift to this theoretical ideal as I repeat the experiment more times. Let me write that down. Drift closer with more reps. Right? If I do fewer, I could get extremely lucky and be right on this. Probably not. I could be much further away with fewer repetitions. Like for example, if I flip it, if I roll the 2 dice once and I happen to get a 3, that's 100% of the time. It's not a lot of repetitions. I'm far away from this theoretical ideal. Okay, so now how do we look at all of these in the table? Well, the number of times that I actually got the outcome we'll call the frequency. Another column here. This fraction, out of the total, how many times I got? It was 20 out of 100. What are the other ones? 2 out of 100. I picked 100 because it's nice and convenient, right? But the total could be anything. 30 out of 100. 18 out of 100. We'll call this the I'll rewrite the relative frequency, because it's relative to what to the number of times that I repeated this experiment. If we add up the relative frequencies, what should we get? 100 out of 100. 1. These relative frequencies are my approximations. Are my approximations of the theoretical probabilities. Now we took a very simple example, one where we can calculate these theoretical ideal probabilities. It's a very simple situation. So simple, I could list all the possibilities I could get. In practice, that's not the case. In practice, one of two things will most likely happen. One is that even though the theoretical probabilities exist, they might be so complicated to calculate that I might not have the mathematical tools to do it. Or it could be a situation that has so many components and is so complicated, I cannot calculate theoretical probabilities. It's impossible. Yet, I want to have an idea for what is likely and how likely. I want to calculate an expected value. I can't calculate an expected value without a probability distribution. If that probability distribution is not accessible to me, which practically is most of the time, what do? I just give up? Like, nope, can't analyze this. No, I run the experiment a few times. Well, a good few times, knowing that the more times I repeat this, the better my approximations will get. I count how many times I got the outcomes that are possible. I calculate my relative frequencies, and those then act as close, I hope, approximations of the theoretical probabilities that I will never see. I will never see these theoretical probabilities. I might never know what they are. I still need to analyze the situation. And out there in practice, things are extremely complicated. Theoretical probabilities that's a luxury that I almost never have. That doesn't mean I should give up. These relative frequencies are the key. Look, for example, at this 18. Now, if I calculate uh, 11 over 36, what is that? 11 over 36. It's 0.3056, let's say. So that's 30.56% approximately. Ideally, however many times I repeat this experiment, around 30% of those times I should get a 6 as the largest number. In my run of 100, I got 18. Wasn't very good. That's pretty far away from 30. Because my 100 is not a lot. It's not a lot of repetitions. 1,000, it's going to be way better. 10,000, if it's practical, way better. And of course, I can do these things with computers, right? So having a lot of repetitions is quite realistic. So these approximations, if I don't have a lot of repetitions, might not be very close to the theoretical probabilities. But I know that the more repetitions I do, the closer and better these relative frequencies will be to the actual theoretical probability. And I can then use this, I can then use this or these relative frequencies to approximate the actual expected value. And remember the expected value, where are we now? The expected value is my first real analysis number, my first real statistical measure to analyze and explain what the situation is, depending on the experiment, whether it's a game of chance or whatever. There are more, and I can then use these relative frequencies. But I wanted to just spend 15 or so minutes just to give an idea of which direction this goes. Theoretical probabilities are where we start, but it's not realistic. It's just not. Things are way more complicated. And people actually think, oh, I roll some dice, I calculate some probabilities. I should always be able to calculate the probabilities. No, you almost never will. But that isn't really a problem. We just need to understand, well, in practice, how do these things actually work? We're always trying to aim for these probabilities. We're always trying to aim for an accurate expected value. And we can get extremely close by just running the experiment, just repeating this a few times. Roll some dice, as many times as you can handle, or simulate it on a computer or whatever. Get relative frequencies, and those can be very good approximations to the actual probabilities that are hidden behind the scenes. And then you can use that to analyze the experiment with really as much accuracy as you need. How do you get more accurate in your approximations? More repetitions. More repetitions. And if I get to 10,000, 100,000 repetitions, a million repetitions, I'm going to be so close to the actual probabilities, to the actual expected value, that it's as good as the real thing. All right. So I'm going to stop here, knowing that we do have a little last bit sort of in this discussion, in this direction, a little bit more to talk about this actual practical side, where I have a limited number of repetitions. I have 100 in my example. Different ways to sort of get an idea for what these 100 repetitions tell me. Not just relative frequencies, not just expected values. There are other little things that are worth mentioning because in real life they do come up every now and then. So it's good things to have in your experience library. I doubt it'll take the whole session, but I don't want to just leave you to it. So a lot of tomorrow will be just Q&A or whatever. Let's just have a look before we stop at our, oh, I have the book here. Let's look at the problems. We have a little bit more to do. We will just solidify the frequencies and stuff like that by way of exercise 7.4. So I'm sort of stopping on purpose. I want to let some things just sit and then we'll do an exercise, whereas other things are done and we will be able to do problems already. So problems you can do right now if you want to. 7.1, 7.2. That's pretty much it. 7.1, 7.2. Theoretical probability distributions, actual expected value, some game of chance, some raffle questions. Those are good questions. I like them. And then when we get to the more practical side of frequencies and relative frequencies, we'll just make sure with some practice tomorrow. Let me just double check. I can also do problem 7.5. That's also a fully theoretical one. And that is it. So 7.1, 2, and 5, if you really want to get to the problems. I guess we do have time, don't we? No, I don't want to. I want you to just let frequencies and let the idea just sit in the back of your mind. Otherwise, we don't have anything to do tomorrow. So give me something to do tomorrow. As it is, I think we have too many sessions. So at least give me tomorrow. So focus on the theoretical side with my raffle example, my dice rolling games of chance where I can calculate the probabilities by just listing possibilities, right? They're not that much. And I can calculate everything precisely. Start with that, practice that, think about that. And then tomorrow we will just see exercises using frequencies instead. Are there any questions or thoughts at this time? No thoughts? Surely you have a thought. All empty? There's no thoughts in there? Void of thought? Just absorbing. I like it. I like it. Yeah, that's important. And if things feel a little confusing sometimes, you'd be surprised. Just let things get processed in the back of your head. We have time. We have time. This is all we're doing for this week. Nothing else is scheduled. Let me look at the schedule actually. That might be a good thing. I'm going to have to update the schedule because we have more time scheduled than I actually can use. Are we now? What is this? This is way too zoomed in. April? No! Get away from me, April. You're not something I want to worry about yet. So we're ahead of the game here. We talked about relative frequencies. Yeah, we didn't even finish really, but we're ahead of the game because we've already covered expected value. It should really be included in the probability distribution discussion, and that's what we did. So Friday is going to be a Q&A session, regardless. We only need one more. So I will update this to be a red block, and then you have reading break coming up, and then another two Q&A sessions. I gave this way too many sessions. So try and not do nothing so that you forget. That might be risky because quiz 2 is quite a long way away after a reading break. So try not to forget anything. But on the other side, there is a lot of time if you need to catch up as well. All right. Until next time. Thank you.